Have you ever wanted to learn how to time travel? You can, if you go mock Jesus. But first, you need to learn about relativity, which is light and space and time doing funny things.
Relativity is highly affected by stars and other masses, such as black holes.
Also, we apologize for any inaccuracies in advance. Now on with the show.
Before you learn about black holes, you need to learn about how they form. So let us start at the beginning, star formation and their life cycle. A star's life cycle is determined by its mass. Pretty much, the bigger it is, the longer it will live and vice versa. The matter in the star's nebula is what determines its mass. The hydrogen gas in the nebula is pulled closer by gravity and begins to spin, heating up, allowing for nuclear fusion in its core. When it collects more matter, it becomes more stable, which is the state that our sun is in right now. I'm so proud. In the core, hydrogen is converted to helium because of the nuclear fusion. This releases heat and energy. Once it starts running out of hydrogen, it ceases heat generation, causing the outer shell to expand, cooling the star and turning it into a red giant. We are going to cover large mass stars from here on forward, which is a star 1.4 to 3 times as massive as our sun. In the core of a red giant, helium fuses to carbon all the way up to iron, resulting in the massive star to undergo a supernova explosion. Because our sun is not a large mass star, it will never undergo this kind of explosion. Anything above 3 solar masses will turn into a black hole.
My turn. You know the sun emits light, right? If you didn't know, that light has a speed. That speed is really fast. Like, really, really, really fast. Mock Jesus. Like, you should be praying for your life if you're going that fast. That speed is around 299,792,458 meters a second in a vacuum. 670,616,629 miles per hour for the freedom people. It is going to be abbreviated as C for the rest of the video. The only thing that can go the speed of light is light, because Einstein said so. C is also the universal speed limit. Nothing can go faster because it would take an infinite amount of energy to accelerate something to C. Also, if you accelerate an object close to C, time slows down for the object, hence time travel, but I'll get into that later. Now, wave-particle duality. Basically, something that is both a wave and a particle at the same time. In this case, light. Light is made up of photons, which are particles. Those photons travel in a wave. The distance between 2 points in the wave determines its wavelength. Therefore, changes how it is perceived. Some different wavelengths include all the colors that you can see, radio, Wi-Fi, and radiation. Okay, fun facts time. Light can travel the circumference of the Earth 7 times in 1 second. Remember, it's fast. It takes light 8 minutes to travel from the sun to the Earth. It would take light about 5 hours to leave the solar system. The closest star to us, Proxima Centauri, or better known as Alpha Centauri, is 4.3 light years away from us. So if you traveled at sea, it would take you 4.3 years to get there. If you were at Proxima Centauri, you would see the COVID-19 pandemic just starting. You are not seeing things as they are. There's a delay between what happens and when light reaches your eyes and is processed by your brain. Okay, I'm done.
Okay, now I want to cover the difference between novas and supernovas. There is more of a difference between the two besides just their size, as their names would probably suggest. Firstly, a supernova explosion doesn't destroy the star. In fact, afterwards, it can continue to gain mass and go through many, many more explosions. Now, a supernova explosion destroys the star, leaving behind one of 2 things, either a black hole or a neutron star. Neutron stars I'll cover after I get into my favorite parts of space, nebulas. But for the meantime, back to Aiden.
Time dilation. That's pretty much how you time travel, but only to the future. Again, because Einstein said so. If you go fast enough, like near C, your time sense will slow down. Travel times would be strange. For instance, 1 year of relativistic travel travel close to the speed of light will be 10 years on Earth. That's pretty much it. The math is really complicated and I won't get into it. But if you want to, Google it. You have the brains to do it yourself.
Now then, neutron stars. Neutron stars are the most dense things in space that astronomers can observe directly. They are formed when a supermassive star collapses, holding a mass between 1 and 3 solar masses. But they are typically only 18 miles in radius. That's all I really have to say about that.
Now, space-time. Space-time is part of the fourth dimension of space. The dimensions of space are width, height, depth, along with time. It works like a blanket. If you put an object in the center of a blanket, the blanket bends around that object. The bigger the bend in the blanket, the more mass that object has. The bend also shows gravity. The bigger the bend, the more gravity it has. If that mass is very big, it will rip space-time and form into a singularity and make a black hole. Now onward to the next topic.
Nebula. Clouds that form after stars go big boom, whether from supernova or nova. The explosion of a star leaves behind much hydrogen and cosmic dust, making for beautiful light shows that are best viewed through a telescope. They are often the regions of which stars form, an example being the pillars of creation in the Eagle Nebula. Star-forming nebula are often referred to as knots. In these knots, there is a good amount of mass, so much so that the dust and gas can begin to collapse into each other. As they collapse, pressure from the gravitational attraction causes the matter in the center to heat up. This creates a protostar, which will eventually heat up enough to ignite and birth a star. Now then, back to Aiden.
Now onto one of the most complicated, weird, and coolest things in the universe. Black holes.
This we're both covering.
Black holes are rips in spacetime caused by the singularity in the center of the black hole.
The singularity is a theoretical point of infinite density and zero volume. That's how it rips spacetime.
They form after the center of the massive star collapses in on itself.
Its gravity is so immense that light can't even escape.
The event horizon is the point where the speed required to escape equals c.
Below the event horizon, we don't really know what happens.
Due to its gravity, time slows down when nearing the event horizon, this is called gravitational time dilation. Now, supermassive black holes
are the center of all galaxies. All the other star stuff orbits it, including our solar system.
These black holes have to be 10 to the 5th or 100,000 solar masses to be considered supermassive.
The origin of supermassive black holes is still a topic that's being researched.
They have thought to have been formed by black holes merging with one another.
Some supermassive black holes are hard to explain because they were dated very, very soon after the Big Bang.
It also has been hypothesized that they could have been formed by a direct collapse of dark matter or by an alternate creation theory called the Big Bounce. Again, if you want to get into it more, Google it! One of the many weird effects when you get close to a black hole is gravitational time dilation. Gravitational time dilation is time dilation due to immense gravity caused by a really massive or dense thing, like a black hole. The bigger the bend in the blanket of space-time, the more gravity. The stronger the gravity, the slower the time passes. For example, if you were approaching or entering the black hole's event horizon, the universe would speed up from your point of view. You might even see the universe die in front of your eyes. On the other hand, if you were watching someone go into a black hole, they would seem to stop. Another one of these weird effects is Hawking radiation, hypothesized by the famous physicist Stephen Hawking. In this process, a black hole would slowly radiate its mass away from itself. This process is called, you guessed it, Hawking radiation. It is a very, very slow process. How it works is virtual matter and antimatter particles are appearing and annihilating themselves in empty space due to quantum physics. When this happens on the event horizon of a black hole, one of the particles is sucked into the black hole and one of them escapes into space and becomes a weird particle. And that is how black holes can slowly shrink over time. Fun facts. It would take a black hole a Google years, which is a 1 with 100 zeros after it. It's a really big number to evaporate completely.
Now then, honorable mentions from me. Pulsars. Pulsars are funny little spinning neutron stars. That's all. Bye-bye.